Hello and welcome to the lecture on quantum numbers which specify electrons and electron states in an atom. So, um, every electron in an atom it will be characterized by four quantum numbers, that is a principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. So, for any electron, these four numbers uh, can't be same. Like at least one of these will be different. Even if, for example, three quantum numbers are same for an uh, electron, for another electron, at least one quantum number will be different. So, specified by principal quantum number, the first one, and which takes the integral values n is equal to 1, 2, 3, 4, 5, and so on, and or it can be represented as K shell, L shell, M shell, and so on. Now, the principal quantum number n it determines the size of an electron orbital. Or the so based on the principal quantum number, we can understand the it will characterize the distance between nucleus to that of electron. So the principal quantum number mainly characterizes. It need not be exact. So for n equal to 1, the subshells will be different from that of n equal to 2. So for 3, there will be another number of subshells. So the number of subshells depend on this n value 0. So only a subshell exists in the uh, n equal to 1 shell. Whereas for n equal to 2 shell, there will be two values possible. That is L equal to 0 to n minus 1, that is 2 minus 1. So up to p subshell. There are two subshells in n equal to 2. And n equal to 3, uh, we have 0, 1, and 2. So in n equal to 3 shell, we have three subshells, that is S subshell, P subshell, and D subshell. And for n is equal to 4, there will be four subshells, that is 0 to 3, that is S subshell, P subshell, D subshell, as well as F subshell. Now so here the shape of the orbital in a subshell it is determined by the azimuthal quantum number. Principal quantum number determines the size of electron orbit, that is distance between electron and the nucleus, whereas the azimuthal quantum number determines the shape of the orbital. So here we have the for s orbital, that is a for s subshell as s orbital, that shape is a spherical shape. As you can see in the diagram in XYZ plane, we have a sphere. That's the s orbital. And whereas p orbital it is dumbbell shape, we have three p orbitals mutually perpendicular to each other. So one is along x-axis, and the other one is along y-axis, and the other one is along z-axis, as you can see here. And similarly for d orbital, it is double dumbbell shape, and f orbital tetrahedral shape. So there are five orbitals. We will see why there are five orbitals as we go along. So here you can see the five, and these are quite complicated compared to the p orbital. Now here we have a d and subscript yz. So which means that these um, orbitals are present in yz plane. Okay, and here it is mentioned xy. That means it is present in the xy plane. And here dz square. Dz square means it is present along z axis. Its motion will be, the electron movement will be along z axis mostly. And then the other one we have here txz, which means along xz in the xz plane, and here tx square y square. So which means it is in the xy plane. It is not exactly. I mean, it's in the in between the xy plane, like this. You can like it is not along the x-axis but in between x and y, and here also in between x and y. So basically here this is the negative y or positive x, and similarly like this in the four quadrants in between the axis it is present. Whereas f orbital is more complex, it is tetrahedral. You can just go through this, and that's not so much important. Like, however, this subscript uh, is there for us to understand in which axis or which plane it is present. So it is basically in the xy plane, and the orientation in the xy plane is also given by these x square, 3y square, and so forth. So this is not so much important, but you can remember how many orbitals present in the F subshell, that is 7. So number of orbitals in a subshell, it is determined by the third quantum number, that is magnetic quantum number. Firstly, the shell has subshells, and each subshell has number of orbitals. So how many number of orbitals are there in each subshell, that is determined by magnetic quantum number. It takes values between minus L and plus L including 0. So for a S subshell, the value is 0. So it is minus 0 to plus 0. So basically it's only 0. There is only one orbital in subshell. Whereas in P subshell, it is from minus 1, 0 and plus 1. So P is equal, the azimuthal quantum number of P is 1. So minus 1, 0 plus 1, that is minus L2 plus L. Hence it has three orbitals in the P subshell. Or in case of D subshell, we have 5 orbitals, and for F, it is from minus 3 to plus 3. So 7 orbitals are present in F subshell. Now, associated with each electron, there is a spin moment based on how the electron rotates uh, along its own axis, not the axis of nucleus, but along its own axis, how we it rotate. Based on that, we have the spin moment that is related to spin of the electron, and that is the fourth quantum number, which is ms, and it takes two values are possible for that. Like if it is rotating in this direction, plus 1 by 2, and it is rotating in this direction, minus 1 by 2. So this is the fourth quantum number. So each electron is represented by four quantum numbers, and they are unique. Like no two electrons can have all the four quantum numbers same. So in Bohr model, when he proposed the Bohr theory, we have got only one quantum number characterizing the electron, that is principal quantum. But as we know that wave mechanics had refined the Bohr's theory, in that process it brought three more quantum numbers. So it was able to completely characterize each and every electron. So Bohr theory was only about explaining the hydrogen atom with single electron. So that's not, it doesn't take much quantum numbers for specifying that only one atom with only one electron. But for atoms with more number of electrons, we need uh, more sophisticated theory to understand, that is wave mechanics. And when we see the energy uh, of different shells, if we look at the shells, we have, based on the principal quantum number, n equal to 1, 2, and 3. So between these three, the one with larger principal quantum number has more energy, whereas the n equal to 1 has lowest, n equal to 2 next, and n equal to 3, and n equal to 4 has more likewise. And within each shell, we know that there are different number of subshells. So how would be the energy between these subshells? Here S has the least energy, then P, then D, and then F. Now, if there is no external magnetic field, then all the orbitals in a subshell, we know that S has one orbital, whereas P has three. So, in the absence of external magnetic field, all the three orbitals in the p subshell will have equal energy. But when we apply a magnetic field, then the subshell states of p will split with each having different energy. For slightly different energy, these three p orbitals will be having. Same with d, same with 5 orbitals in d subshell and 7 orbitals in f subshell. Okay, thank you so much for watching this video. Uh, Please subscribe this channel for getting more videos. Thank you.